Welcome to week 5 of Introduction to Research Design and Methodology. I am Jeff Boggs. Last week in class, we discussed Spickard's 12 data collection methods that he outlines in his 4th chapter of the textbook. Remember, we care about data collection methods because in order to answer a specific research question, so our research question, we need to pick a data collection method that's appropriate for collecting the data that we actually need to answer that question, and not data that would answer some other question. So these 12 data collection methods were public and private records, and in particular, visiting archives that contain public and private records. Detached observation, which takes a lot of different forms and which is the de facto mode of data collection in physical geography. Ethnography or participant observation, in-depth interviews, surveys, and questionnaires. So surveys and questionnaires are something that you've all filled out. So most of you in this course, when you completed the survey at the beginning of the semester, that was an example of one of these. Phenomenological interviews, critical incident interviews, focus groups, psychological scales, or what I've called psych scales, but psychological scales, and content analysis. So you'll notice that 4 of these have little red dots next to them. Oh, sorry, I left off discourse analysis and grounded theory. But the 4 with the red dots or asterisks next to them, these are the data collection methods that are most appropriate for the 3-day field course based on past practice, past behavior of previous years of students in that course. This week, we are going to talk about Chapter 5, which deals with data collection sites. And we will unpack what we mean by data collection sites because it can have really 2 different meanings. Remembering that Spickard identifies 6 steps for answering your research question. Let's cover those. So the first is to develop a good research question. So that is one that is focused and it's somewhat clear about what you are asking and even implies what kind of data you need to collect. Then we choose a corresponding logical structure. He identifies 10. We then identify the type of data you need to answer that research question. He identifies 14. We then pick a data collection method. That's what we did in the last lectures. We discussed those. There were 12. And then we choose a site and a sampling strategy. So where do we find the data? That really gets at this notion of site. And sampling strategy is given all the possible observations we could make, how do we choose which elements or which items in that population to sample from? And then finally, we pick a data analysis method. And so you'll notice that for 5 and for 6, for steps 5 and 6, he does not provide as many kind of categories as he did for chapters 2, 3, and 4, but that's okay. So just to be clear, this week we are focusing on site and sampling strategy. So what is a data collection site? A data collection site is a location that contains the data that you need to answer your research question. So it is a place, if you will, a location that has the data that you need to answer your research question. And Spickard talks about how it's useful to distinguish between actual sites of interest and data about those sites. So sites of interest are the places, the locations that we're interested in. So that's often where whatever it is we're interested in is actually happening. But sometimes there's data about those places, there's data about those sites, there's data about those locations that is found somewhere else. And this provides us a kind of a segue into the difference between primary and secondary. At this point, we have a segue to talking about primary and secondary data. So Spickard has talked about this a little bit, but it's useful to go back over this. So primary data, remember, that's data that you collect yourself. That is data that is collected at the site of interest. If I'm interested in how people behave at dog parks, then if I want to collect primary data, I should go to the dog park and conduct maybe or use, say, detached observation or questionnaires as ways to collect data. Secondary data are data that someone else has already collected. So secondary data, the nice thing about it is that I don't actually have to go to the site of interest. So for people that are interested in, say, global climate change, they don't have to go to every point where data was collected. They instead have to go into an archive or a repository and acquire the data there. At this point, you want to ask yourself, do the data you need exist already? At least normally. When you go to Peterborough, you're going to engage in primary data collection because that's part of how the field course is set up. But generally, we want to think about, do the data that I need already exist? Because if they do and someone else has them, then maybe you can just use their data, which can save a lot of time and work and money. So if the data exists already, here on our little flow chart, that means that secondary data exists. So if that data already exists, if someone already has collected data on the St. Catharines Dog Park over on Russell, or by the Russell Community Center, and that data exists, that means that I might not need to collect any data. So that means that secondary data exists. If the data I need don't exist, so let's say I was looking at a dog park in Welland or Fort Erie or Toronto, if the data don't exist, then I have to collect those data. I have to collect that data. For what it's worth, data is generally, some sticklers will see it as a plural, whereas in North America, lots of people use it interchangeably as both plural and singular. So you'll hear me switch back and forth between using data as a singular noun or as a plural noun. Okay, so if the data don't already exist, you have to collect it, and that is primary data. However, if we go back here to secondary data, just because secondary data exists, this leads us to that can you have the data question. If yes, then that's amazing. You're really lucky. If no, then, so yes, just go and get the data. If no, then the question is, can you access the site to collect your own data? Which is actually then a question that flows off of this no over here as well. So if the data don't exist, then the next question is, can you access the site to collect your own data? But also, if the data exists, but you can't have access to those data, then the same question that you have to ask yourself is, can you access the site to collect your own data? All right, at this point, then we ask ourselves, Is the answer yes? So I can go to the dog park and I can collect my own data. If this were me conducting research, then my next step would be, after I kind of sketched out my research proposal, is then I would submit a REB, Research Ethics Board application to Brock University, because I am beholden to do that with any research that involves human subjects. So even if I just go and watch people at a dog park, I need to get approval to do that. If you're a physical geographer, you can often get around that because you're not dealing with people. At least the actual collection. You still might need to deal with people as a physical geographer if you need to get onto the land that has the site, or that has the data, right? So can you access the site to collect your own data? So if you need to get into a particular field and take soil samples, and the farmer who owns the field says, no way, get off my land, then you cannot access that site, right? The other possibility is no. So there's no data, or there is data, but nobody will share it with me, and I cannot get to that site that has the data. If that's the case, then I need to find myself a new research question, which that's very unfortunate. But if you can't get data, you can't answer your question. That's the long and short of it. When it comes to collecting secondary data, there are a couple of kinds of sites that you will become familiar with. And often you'll become familiar with them having conducted a literature review. You will see where other researchers have acquired their own secondary and also their own primary data. So that's one of the benefits of a annotated bibliography and a lit review, is that it helps you understand how other people who have been asking questions somewhat similar to yours, how they acquired their data, what they had to do to acquire their data. So secondary data is usually increasingly some kind of data set if it's quantitative data, so like climate data or various kinds of economic data, or it can also be in archival records that might be held by a government agency or a private organization. So an example, I guess, of government archival records might be birth certificates or death certificates held by whichever branch of local or provincial government is responsible for counting births and deaths. But private groups might also have archives as well. So you can find archives that are based around famous authors and the correspondence, so the letter writing that they engaged in. Firms will often have, especially old firms, will often have an archive, or trade associations or professional organizations will often have an archive that sort of provides primary data on, well, actually, I guess in this we might think of it as sometimes, well, let's stick with that for a second. So in which you can find archives that will have data about how a particular firm behaved over time, if you were interested in firms. Property records might be held by particular private groups or nonprofit groups like a nature conservancy. But the point here is that the data has already been collected and compiled somewhere, and that it's often lots of data. And the way that you gain access to these is by traveling to wherever the data is stored. So this might be libraries, this might be archives. Increasingly, though, it is online, especially for data produced by nonprofits like the World Bank or governmental bodies like Statistics Canada. For my own dissertation research, when I was doing pre-dissertation research, I went to archives that were run by a trade association in Germany. Gosh, I can't even remember the name of it anymore. It's this really long German name. It's basically Die Deutsches Buchverein? No, the Börsenverein des Deutschen Buchhandels. That's what it was. So basically the exchange of German booksellers. It's a bad translation of it. But they had data that went back quite a long time. And I needed it so I could map out the number of book publishing houses that were operating in Germany before the Second World War. And I needed to do that because there weren't the government data. There wasn't very good government data. So that was kind of just before the Nazis and then during the Nazis. But in a lot of countries outside of North America, borders have changed over time. Governments get overthrown violently, and that creates lots of problems for, among other things, government documents or government records. So if you decide that, you are like, if you lose a war and a big chunk of your country gets given away to another country, because that's how things work in wartime, all of a sudden, all the records that you had on that place that's now part of another country, it's useful for historical reasons, but it doesn't, you don't know anything after that time that country A lost part of its land to country B. So, and then in a European case, this often went back and forth. So it's a nightmare in that situation. And so with secondary data, problems can arise with comparisons between years and locations, especially if there's a new government. And especially if there's a new type of government. So these are things to bear in mind when you are collecting secondary data. If you are going to make use of secondary data, there are some common problems that can crop up. Some are that data is just missing. So maybe mice ate all of those birth certificates, made a big nest out of them for the years 1903 to 1907 in a particular location that you were interested in. And if that was the only place those data were held, that's your tough luck, right? A more modern problem is that data can be corrupted by software errors. And that's why it's often useful to have multiple copies on different computers of the same data set. Sometimes data is collected for a while and then no longer collected. So for instance, in the United States, in the early 1980s, there had been strike data that had been collected annually, I think starting under Franklin Roosevelt, FDR, starting in like the mid 1930s as part of the New Deal. And then in the early 1980s, Ronald Reagan's government decides to stop collecting strike data. So sometimes there can be ideological reasons for why data is or is no longer collected. So we see this in the Canadian census fiasco of 2011. We see this in a lot of cases with environmental data where governments that are opposed to recognizing climate change will just stop funding the collection of those data. So this is another thing to be aware of. A thing that can also happen is that the way data gets collected can change over time. So in StatsCan, or Statistics Canada, so StatsCan is a sort of shorthand for statistics, or StatsCan is shorthand for Statistics Canada. In 2011, the National Household Survey was declared to be no longer obligatory, but instead optional. So if you didn't want to fill it out, then you didn't provide that data. But then the problem with that is that Statistics Canada data is used to allocate money throughout Canada and to understand changes in sort of changing ethnicity, education levels, demography. And so by making the household survey portion of the 2011 census optional, that meant that some chunk of people did not reply, and enough people did not reply that it basically made the 2011 National Household Survey a waste of money. So another thing that can happen is that your geographical units change. So in the 1960s, Ontario began shifting from, I mean, there are still counties in Ontario, but in the 1960s, there began to be a shift towards creating what are called regional municipalities that, in the case of Niagara, for instance, amalgamated two different counties. So I think it was Welland County and Lincoln County were squished together to become the regional municipality of Niagara. So these are kind of common problems with secondary data that you want to be aware of as you're making use of it. Speaking of Statistics Canada, it's useful, especially if you're in geography and tourism studies, to know a bit about the kinds of geographical categories that Statistics Canada makes use of. So you can think of these as sort of like buckets or containers. So demographic data, for instance, is available at many scales. So, average household size, the mean age of the population, the number of people between the age of 0 and 4 by sex, all of this stuff is available from Statistics Canada, and it might be that that's useful as kind of background information for your field project in Peterborough, that you'd still also want to collect primary data. So some of the more common scales at which these data are collected and disseminated are something called a dissemination area, and that has up to a few thousand people in it. There's something called a census subdivision, which is bigger, and census subdivisions in Ontario correspond to the boundaries of municipalities. So census divisions are even bigger than census subdivisions, and in Ontario, these correspond to regional municipalities often. So for instance, in Niagara, there's 12 census subdivisions because there are 12 municipalities. So we have 12 CSDs, but there's only one census division in Niagara because there's only one kind of regional municipality that sort of sits over all of those. Then they'll also provide data. There's other scales as well, but these are really common. So at the provincial level, so all of Ontario, and then at the federal or national level for all of Canada. And it might be useful to think of these as, we're going from the smallest area to the largest area. And if you're really interested in Statistics Canada data and how to use it, I teach a third-year course called, it's either 3V61 or 3P61. We kind of renamed it, and it's called Using the Canadian Census. So feel free to take that course if this stuff wets your whistle. Things that you want to think about when you're collecting primary data, and to be clear, when you get a Peterborough, that's what you're going to have to do. And for the research proposal for this course, I want you to write a research proposal that involves the collection of primary data. So you want to pay attention to this. So things to be aware of when collecting primary data is that, if you can't find this appropriate secondary site, literally the meaning of the word site changes, because it now becomes both the site that interests you. So if I stick with dog parks, a particular dog park, or dog parks in general in a city or even in a part of the province, if I think that dog parks share some similarity. So those are the site or sites that would interest me. But they are also the sites where I would have to collect data from users of dog parks. So the key point here is that for primary data, there's a location or locations that you're interested in, and you have to go to those places, to those locations, to collect the data. At this point, I find it useful to begin to discuss terms like samples and populations and how those are similar and how those are different, and some other related terms. So I would recommend that if you're not already taking notes, that you take notes in the next couple of pages to have a firm grasp of the difference between a sample and a population. So this slide is sort of a holdover from when I teach the class in person, but we'll use it for now in so much as it helps us think about what we want to focus on. So customarily, I would have students sit down and write down these terms. So population, sampling frame, sample, random, representative sample, and biased sample. And I would ask them to sit down, take a couple of minutes, and write out definitions to these based on their current understanding. And then that's the thinking part. So this is a common pedagogical technique. And then after they thought about it, after they had written down their thoughts, then I would have them pair up with one of their neighbors, or maybe a couple of their neighbors, and share with those neighbors what their definitions were. So they could then start to have, so students would then begin to discuss what these terms mean, which then might also help them remember. I mean, and also in a real class, this is a useful skill, or not a useful skill, it's a useful technique to get otherwise shy students to talk to each other, right? So the next couple of slides, I'm going to talk about populations, samples, sampling frames. What do I mean by random? What do we mean by representative sample? What do we mean by biased sample? Now I'm looking at these and wondering, why did I not capitalize the first letter of all of these? Oh well, won't kill anybody that they're not all capitalized. Okay, let's go on. So the first question we want to ask, and this will help then you develop definitions of these, is what is the relation between a population and a sample? So let me say this in words first. So a population is all of the elements in the population, which sounds kind of strange, but bear with me. A sample is a subset of those elements. So a population is, if it's the population of the Niagara region, that's around 450,000 people. Literally, those are, and if those are all the residents, then the population of the Niagara region is 450,000 people. That means that it's everyone who lives in the Niagara region in this particular case. It could be the population of all frogs in a pond, which might be 23 frogs, right? So a sample of Niagara residents would be some collection of people less than 450,000 or thereabouts, right? So it would not include everyone. It would just be a subset. A sample of frogs in a pond would be, maybe half the frogs, 3/4 of the frogs. Even if there are 23 frogs, a sample with 22 frogs. As soon as you actually have data on every element of the population, be the population of people or frogs or anything else, that is called a census. Okay, so we've got populations, that's everybody or everything in the population, and we usually want to draw a geographic boundary around that. And a sample is just a subset of that population. So here we have, I want to say this is 50. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Actually, here are 40 people, right? So this is our population. So a sample, here we have a sample with 2 people in it, right? And we have not yet gotten to how we select our sample. That comes later. So here we have a sample of 2 people from a population of 40. If we take 3 more, then we have a sample of 5 people from a population of 40. There's 2 more, so there we have a sample of 7 people, 1, 2, 3, 4, 5, 6, 7, from a population of 40. There's an 8th person, so there's 8 of the 40 people, so that's 20%, right? So because 8 goes into 40, it goes into it 5 times, so 1/5 is equal to 20%. So that's a sample of 20% of the population. Here's a sample with 9, with 10. So the point here is that a sample is just a subset of a population. You want to commit this to memory. So that means just memorize this. So a population consists of all of the elements. So in this case, there are 40 people in this population. Each element is a person, and a sample is just a subset of that population. If we included the entire population, then that's generally thought of as a census. And so in Canada, every 5 years, there's a census that asks usually about the same 10 or so questions of everyone in the population. And it's a household census. So each household receives a census form and is asked to complete it. And then on top of that, depending on which year it is, usually 20 or 25% of all households also receive a longer survey that goes along with it. It's with a mandatory response required. And for the census in Canada, that's also by law requires a mandatory response. And I know you've been taking notes about the difference between a sample and a population. I want you to continue taking notes now to think about the two basic types of samples or sampling procedures. And these are random and non-random. Sometimes random gets called a probability sample, and a non-random sample gets called a non-probability sampling, or a non-probability sampling procedure, or a non-probability sample. And the definition of random is very precise in this case. It is not this sort of garden variety usage of the term random that is common in North American English. So random means that every element in the population has an equal chance of being selected. Random samples are usually used with quantitative, when you are collecting quantitative data. And hold on here. So random, so remember this is, let me write up here. Each element in the population has an equal chance of being selected. And so in our previous example where we had a population of 40, that means that each individual has a 1 in 40 chance of being selected, right? So 1 out of 40, which I want to say is, I think it's 2.5%. Somebody might want to check that actually. Let me pull up a calculator here out of my desk. I guess I'll use my phone. I have to say I hate using my phone as a calculator just because I have to find the calculator button, but I'm pretty sure that's 2.5%. Hold on. Screw it. Okay, we'll say it is 2.5%. That feels right. Yeah, okay. Okay, we'll leave it at that. So random samples are usually associated with quantitative research. Occasionally, qualitative research will use random samples, but that's really rare. And the reason that we would want to use a random sample is that we want to make inferences about a population that's providing the sample. And you would cover this more in a statistics course, but I've taught a bunch of those. So for now, kind of take it on faith, if you will, that random samples are what you need if you want to generalize from your sample to the population. So I believe, so down here, the goal is generalizing. So we want to be able to say that what we see in the sample is probably what we would also see in the population. So the goal is generalizing, right? All right. So non-random samples typically are, so qualitative research usually relies on non-random samples as a rule of thumb, though there are also some kinds of quantitative, so I put quant here instead of quantitative as a shorthand for, so those mean the same thing. So some quantitative research will also rely on non-random samples, which is fine as long as you recognize that what you're talking about is really just specific to your population and that you don't have a good mathematical basis for generalizing to a larger population from it. But sometimes you don't, sometimes you would like to have a random sample, but you can't. And so in that case, you'll make use of a non-random sample. And there are other times when it doesn't matter and that actually you literally don't want a random sample, but instead you want to be more picky about who makes it into your sample. And in those cases, you would choose a non-random approach. It could also be that you can't be bothered, and in those cases, you usually go with non-random. So my understanding is that in a lot of cases for Peterborough, especially among human geographers, they will tend to rely on non-random samples because of problems associated with developing a sampling frame, which we'll talk about here in the next couple of slides. In physical geography, you often rely on random or de facto random samples, often collected through something like the use of a grid or a transect. As a way to sort of randomize your data collection. So with the transect, you identify some locations, so literally kind of lines. Maybe they're like, 5 meters apart. So 5 meters from there to there. And then maybe every meter along that line, you would take a reading with a Schmidt hammer or a soil sample. And you do that kind of systematically across an area. So this is these are 2 transects. And then from those data, then you calculate some statistics like means and standard deviations, which may not mean anything to you right now. So, but that's fine. With the grid, and we'll talk more about this probably in week 6, a grid, you basically literally draw a grid on an area. So, and so pretend each of these squares is the same size. And that's horrible looking. But I am still getting better with this pen. So here we have 1, 2, 3, 4, 5, 1, 2, 3, 4. So we have a grid of 20 areas. If we pretend that those are all of the equal size, then we might say, okay, we are going to put bug traps, there are fancier terms, in 5 of these. And so we randomly select, so we might put, number each of these squares from 1 to 20, get a 20-sided die. I think that's a dodecahedron. So if you play Dungeons and Dragons, you're familiar with 20-sided dice. Roll the die 5 times and re-roll if you get the same number twice or thrice, and use the 20-sided die to pick your spots where you place your bug traps. And then you'll collect bugs from those areas, right? But instead of sampling all 20 grids, you would just be sampling, in that instance, 5 grids. think that is everything on this slide. Oh, one more thing. So, and you should still be taking notes. So for quantitative non-random samples, remember that the goal is not to make inferences about a larger population. So you are not generalizing to a larger population. Okay. So we've talked about samples, we've talked about populations. So you have a sense of how populations and samples are now related. You have a sense of the difference between a random and a non-random sample. So in a random sample, every element in the population has an equal chance of being selected. In a non-random sample, that doesn't hold. And this then provides us a segue to talk about representative samples. So lots of people will ask, okay, if it's a representative sample, that sounds really cool, but what does that actually mean? What does that sample represent? So what it represents is the properties of the population from which it was drawn. So one way to think about this, so it could be properties or characteristics. Right? So it represents the characteristics of the population from which it is drawn. If we think in terms of soil samples, for instance, then, a characteristic could be something like, so for soils, might be pH level, right? So how acidic or base is that soil? It might have to do with, water content. It might have to do even with soil structure. Using that funky triangular table that soil scientists love, right? For people, put humans, right? It might be age, these properties. So age could be a property, like sex or gender. Height, this is a good one to use when you actually have a real class, not that you're not a real class, but when you have an in-person class, is that you can sort of randomly sample everybody. So maybe take every fourth person that's just set up in a line that's been composed willy-nilly and use that as a sample to measure the height, so of that sample, but then also use that to make inferences about the population. And also in a class, you actually have everybody's height. So usually people will talk about their age and their height pretty easily. You don't want to ask people about their weight in a class. I'm talking to future educators here, because in North America, people are often kind of sensitive about their weight, right? So age, weight, you wouldn't ask this in a class, but another characteristic might be income, which is sometimes related to years of education. So these are characteristics that, in most cases, for people at least, so these 1, 2, 3, 4 are all numerical. So it could be your age in years. That's usually what we ask. It could be your height in meters, your income in Canadian dollars, years of education in years, right? So these are all numerical data. And later we'll talk about different kinds of numerical data. And over here for soils, the pH, I believe, is calculated It's a numerical value where 7 is neutral. I think it goes from 0 to 14, and it is on a logarithmic scale, but it is a number. Water content, the percentage of, you could, well, an easy way would be to say, for, 10 centimeter sample of water, how many grams of water are in it. Soil structure is a bit trickier because soil structure is based on a table that looks kind of like that. And it has, I can't remember which goes where, but like clay, sand, and silt, I think goes there. I could have the locations mixed up, but then it gives us a weird set of numbers. So let's pretend this is silt, even though this is, I'm sure this is wrong, clay and sand. I believe those are the components that go into soil. And so, this goes from, say, 0 to 100, 0 to 100, 0 to 100. So this technically gives you 3 different numbers. But what all of these then have in common is that they're numerical data. And so a representative sample represents the properties of the population from which it's drawn. And often those are going to be things that are easily measured numerically, right? So we could also ask questions like, hair color. Or, ethnicity or race or, language spoken at home. And those are data that can also be converted into numbers, but they're less precise than measures like age, height, and income or years of education. So for soils, I suppose we could also have color, right? Which often will then be related to the composition of sand, silt, and clay. But again, color is harder to convert into numbers. It's not impossible, but it's can be trickier. So I guess the subtext here is that when you are getting a representative sample, you want to think about, are your data primarily what are called interval or ratio level measures, or are they nominal or ordinal level measures? And we'll talk about those later, I think next week, what that means. Anyway, so a representative sample represents the characteristics of the population from which it's drawn. And the way that we get a representative sample, hold on. Oh yeah, look here, years of schooling, gender, so as some examples. So, and on average, what we find is that representative samples produce best estimates of a population parameter. So this starts to take us off into the land of statistics, which is totally cool, but is not really this course. So an example, a best estimate might be mean age of all the students in a class. And one way that we can show that is sometimes people will draw a bar over a mean that's drawn from a sample. Whereas the population parameter, get rid of that, let's get back over here. The population parameter will refer to the mean age of the whole population. Whereas the estimate is going to be the mean age, so of the sample. And there's something called the central limit theorem which lets us be relatively precise in our understanding of how likely our sample is to represent the actual characteristics of the population. So basically, if it's a representative sample, which actually is always going to come from a random sample, then that will produce the best estimate of this population parameter, which is just the population, I guess the characteristics of the population. But sometimes it's hard to, like if you have a small population, it might be possible to actually measure everyone in that population. But as your population gets bigger and bigger, it becomes more difficult to measure everyone in that population for a range of reasons. So we'll kind of leave it here. So let's say a bit more about representative samples. So here we happen to have an example of a population that has 25 people. So hold on. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there are 25 people in the population. Sometimes we will write that as a big N, a capital N. So capital letter means it's the population. So N is equal to 25. And over here, we happen to have a sample in which N is equal to 6. And so you'll notice here that I've got a big N for, oh, hell's bells. Let me fix that. We've got a capital N, big N, right? It tells us that that's the sample, sorry, that's the population size. So the big N means there's 25 people in the population. Well, a lowercase n tells us this is a sample with 6 elements, or in this case, 6 people in the population. And so in this population, we have people who are, some of which are black, or people of color in general, and other people are white. So we could also say, you know, that one group speaks one language, one group speaks another language. So, and so in this population, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 people who are white, which means that we should have 10 people who are black. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we've got our population, and we know that in that population of 25 people, 15 are white and 10 are black. So in this case, this pi is the symbol that they're using there, which I don't use too much except for when I'm doing geometry, but pi can also be used to refer to the population proportion. And this follows a more common convention in statistics of Greek letters refer to, I'm probably going off the rails here, but so Greek letters mean that it's a population, and so a population parameters, where Latin letters, so the letters used in English, equal a sample, and so in their lowercase. So here's kind of an exception. I'm not sure what the Greek sound for N is, but I doubt if it's a capital N. Anyway, so we see here that in this population, 60% or 0.6, so of the population are white, meaning that 0.4% of the population are black. If we take a random sample, we will typically get a value that is close to the population parameter, so to the actual value. So here's an example in which this sample happens to have 6 people in it, so it's sample size 6, and it has captured, so 2 black people, 4 white people, so the lowercase p, so the proportion of white people in the sample, in this case, is 0.67, right? So 2/3, which is relatively close to this value, right? So 0.67 is our best estimate of, in this case, pi, this proportion. Now, you could pick a sample randomly. So if it's if there are 25 elements, that means that every person in the population has a 4% chance of being selected. So it's possible that your random sample could pick all black people or pick all white people, but on average, if you take repeated samples of size 6, you will tend to get a value that's pretty close to 0.67. And if you took repeated samples of, say, size 5, you would get values that would tend to be closer to 0.6. Oh, would that be right? Hold on. Yeah, because if you would have 3 white people and 2 black people. So this doesn't mean that every sample that's selected is going to be 0.67, but on average, repeated random samples will produce an estimate that's relatively close to this population parameter. Now, you might ask yourself, well, if we already know this, if we already know that there's 25 people and 10 of them are black and 15 are white, then why do we need to know this over here? You probably don't, except that if you are taking a sample and you want it to capture proportionally the number of white and black people, then that actually might be useful knowledge to know, right? So, but I don't want to go too far down this rabbit hole. This is more of a topic for a full-on stats course. I guess what I want you to remember is that representative samples usually produce estimates that are close to the actual population's measurement or the actual population parameter. And this usually, we can actually come up with sort of a way to describe that in terms of confidence intervals or in margins of errors. So I guess a margin of error captures this usually, whereas the confidence interval tells us the size of the confidence interval, tells us how close it is or how likely it is to fall within there. But I'm sort of muddling stuff together. So the point here is that representative samples, we like them. And remember, representative samples are random. And that every element has a 1 in 4 chance of being selected. So for this, if there are 25 people, every person has a 1 in 25 chance of being selected, which is, 4% or 0.04, if you like to think in terms of proportions. And so representative samples usually produce estimates that are close to the population's actual parameter. And the kicker here, the thing to bear in mind is that the sample, oh my God, must be random. So So in your proposal, if you want to engage in random sampling, then you are going to want to be able to tell me something about your sampling frame. And we'll get to that, I think, in the next slide. So what is a random sample? I've sort of already given the story away. A random sample is the same as a representative sample. Or, sorry, I guess a random sample is likely to produce a representative sample. So, and that it captures the true distribution of the underlying characteristic of the population, that's captured also in the sample. So we have a random sample, and let me turn that off there. So a random sample means that each element in the population has the same chance of being selected. So in the previous slide, there were 25 people. Each person has a 1 in 25 chance of being selected. So when we say element, that's kind of the generic term for people, or I guess I had an earlier example with frogs, right? Let's draw a frog. So there's my frog. Ribbit. Right? So it could be a soil sample. I don't know how to draw dirt very well. It could be a tree. That could be an element. So if your population are all the spruce trees in a particular forest, as long as you can precisely define the boundaries of that forest, then in theory, you could take a census of that forest for all of its elm trees and record their location, their height, core each of those trees to use dendrochronology to understand how old they are, right? So a tree then could be an element in a population of trees. This actually is a coniferous tree. Elms are not coniferous, so this would be, I don't know, like fiddlesticks, like a pine tree of some sort, right? So this would not be an elm. So pine, not elm. Pine trees are just easier to draw. Okay. So what this means then is that any sample that is not random is biased, statistically speaking. So biased is a word that gets bounced around a lot in English, but biased, when you're talking about samples, you want to be specific about what kind of bias you're talking about. So here is if it's not random, it's biased. This means each element did not have the same chance of being selected. And there's a lot of things that can cause that. So with people, there can be a response bias. So it might be that there's some characteristic of people that make them more or less likely to respond to a survey, for instance. Or if we think in terms of frogs in a pond, it might be that a response bias is that I don't want to jump into water that's any deeper than a meter, because after that, then I'm likely to then just get completely submerged. And so that might not be a problem if the pond is only less than a meter deep, but as soon as the body of water is over a meter deep, then there will be a kind of, I suppose that's more of a sampling bias, but we could think of that in terms of a response bias. So it's not as if you go up to the frog and say, "Hello, Mrs. Frog, would you like to participate in my scientific study?" Frog is just going to say ribbit, right? So you have to catch the frog. So this might be more of an example of another kind of like sampling bias. But in a way, we can think of it as a response bias in that frogs that are in shallow water are easier to catch than frogs that like to hang out in deep water, right? And so it might be that younger frogs tend to hang out in shallower areas and older frogs might hang out in deeper areas. And so what we might find is that we actually have, that frogs in the middle of the pond, because it's deeper, have a lower chance of being selected than frogs on the outside edge of the pond because they're easier to catch. Okay. I think that's everything for this slide. Oh, yeah. This point down here is to avoid confusion, be careful using the word biased or random. So I want you to write this down. So in your proposals, you are probably going to be tempted to use the word biased or random. So remember, only use the word random if you really mean that each element in the population has the same chance of being selected. A way to say that mathematically, if we go over here, is that every element has like a 1 in chance of being selected. So if your population has 25 people, then this means that everybody has a 1 in 25 chance of being selected, right? If everybody doesn't have a 4% chance of being selected, so 1 in 25, then it is no longer random. But it is instead a biased sample, so it's a non-random sample. But then biased, there are different kinds of biases, so response bias is one. Sampling bias is often like a more kind of catch-all term. But what I want you to promise me is that you are not going to use the word biased or random unless you mean it in a very precise way. That being the way it's described here. Okay, we shall proceed to the next slide. Let's imagine that you would like to collect a random sample. So if that's what you want to do, there are some basic steps that you need to follow. First is you need to identify the population. So are you interested in frogs? If so, what kind of frogs? And often, well, actually in practice, where are these frogs? If you're interested in people, what kind of people? Where are these people? Are these, people who have children? Are these people who have attended university? Are these people who are new Canadians? Are these people who work in the service sector? So you want to be fairly specific about who your population is. And then after you've thought that through, and often identifying your population, you want to look back at your research question, and that will often inform you as to who your population is. And then you want to identify a sampling frame. This, in my experience, is the kicker. This is the difficult thing. Sometimes this is a list. So historically, human geographers and tourism studies scholars have made use of lists like telephone books. If you were going to survey people on the telephone, you could literally go through the phone book, pick every 8th person or every 32nd person or phone number in the white pages of the telephone book. And then you would have, so your sampling frame would be the phone book, and your sample would be, every 8th or 32nd or, whatever number you started with, and then skipped systematically through that list. That would be, that list would be your sampling frame. In the United States, registered voters are registered and those lists are publicly available, so those can be used. In Canada, I don't believe there's quite the same thing. But, there are often lists. So let's say you work for a company and you have a list of all your clients. So that list could be a sampling frame that you then, randomly sample from. And, maybe you, in that case, maybe your list only has like 200 people. And so you take a little, you put a number next to everybody's name, you cut out 200 squares of roughly the same size, number them from 1 to 200. So each square, each little piece of paper corresponds to one individual on the list. Put that into a box, shake up the box, and then, pick out, I don't know, 15 or 40 or 3, whatever, how big, it depends on, there are a couple of things that shape how many observations or how many elements you select, but for the sake of argument, we'll leave that for later. And you pull numbers out of a hat, basically, or out of a box, or if you think in terms of lottery, hold on, we'll come back to this in a minute. If you think in terms of lotteries, they will use devices that spin balls that are then randomly selected, and those numbers are kind of lined up. So in that case, for the lottery, the sampling frame is, let's say that they can distribute up to 10 million tickets a week. Then their sampling frame is all the tickets from 1 to 10 million, right? Okay, so a list is a big one. And then we decide on a sampling procedure. And RNG stands for random number generator. So this could be, So an RNG, like pieces of paper roughly the same size in a hat, that's a crude random number generator. There's also software and websites that generate what are called pseudo-random numbers. Some older textbooks will still have lists of random numbers. They'll have random number tables in the back of the textbook that you can use. So that's certainly one procedure. Another that I've made use of is called systematic. And so this is where you have a list, for instance, or a grid, and you say, okay, there are, on this list, there are 200 people. I need a sample with, for the sake of argument, 20 people. So I'm going to pick a random number. I'm going to generate a random number from 1 to 20. In this case, I would roll a 20-sided die. And let's say that it's 15. So that means that I start on that list by looking at person 15, and then I go to person 30, and then I go to person 45, and then I go to person 60. So that is an example of systematic sampling, which produces a de facto random as long as there's no kind of underlying pattern. So long as every 15th person is not, distinctly different from everybody else in the population. So what else? Yeah, chits in a hat. So this is basically, pieces of paper with numbers on them that you throw into a box or hat and you pull those out. So these are common ways to generate a sampling procedure. So systematic can actually also involve transects, which I illustrated a couple of pages ago. Okay, what do we have next? Then after so you've got a sampling frame, so you've got your list, which actually could be a map or a grid, but I'll give some examples of those later. I mean, I did earlier, but I think one of the Sakai examples will go more into that next week. So then you decide on a sample size. So how many observations, how many elements do you need? And this is going to depend upon some formulas that we're not going to talk about right now. But a rule of thumb that I've seen used a lot is that your sample size should be at least 30. Though there are ways to get around that. But if you have a random sample and you don't have time to calculate some other finicky bits, then go with a sample size of 30. Because I don't have time to explain all of the intricacies of this. That's something more that comes up in a stats course. Okay, hold on. What else? Is that it? Oh, yeah. All right. Yep. So 38 or more. And then you draw a sample. This means that that's a weird verb in English. So it's sort of like a horse draws a cart. So you either use a random number generator or you generate a random number, maybe using dice, and begin your systematic sampling, or you have chits in a hat and you draw samples until you get to whatever your sample size is. And the reason we do all of this is to estimate the population parameter. And what's cool about this, sometimes it seems like witchcraft or voodoo, but is that very often a random sample produces an estimate so your textbook does a reasonable job of discussing 3 concepts that are related to estimating from a random sample. And I don't want to spend a whole lot of time on this because, again, this is something that you'll cover more in a stats course in your 3rd year, but there's sample size, margin of error, and confidence level. So sample size, we've already covered that, right? That's, small n, well, hold on. Yeah, it's the number of individuals in the sample, right? So it's the, if you will, the small n. So n equals some number. Margin of error, you've probably seen this most frequently in political polls. And so that tells us a range in which our estimate falls. So it could be that, if we're thinking in terms of weights of frogs that we were catching in a pond, then, maybe frogs on average. So for let's say that we captured, in this case, 15 frogs out of the 27. I think I said there were 27. And that we find that, their average weight is like 30.2, let's say it's 130.2 grams. So those frogs weigh a bit more. Let's say these are big frogs, 430.2 grams, right? So these frogs are almost a pound. These are pretty large frogs. So that 430.2 grams would be our mean or average weight for all 15 of those frogs. You take all 15 frogs, add each of their weights together, divide it by 15, it would give us this. Actually, if it's a sample mean, you would then also, nope, that works. I'm thinking of something else. Okay, yeah, so 430.2 grams. And the margin of error in case of these frogs might be that, we think that our margin of error is plus or minus 57.5 grams. So we have this thing here, which is our point estimate. And then what this means is that frogs are going to be from, this is where I need my calculator again, so 430.2 minus 57.5 to 430.2 plus 57.5. Hold on, let's do this here. So that would be what, 487.5, and this would be, no, fiddlesticks. Hold on. Okay, 30, so 27, so that's going to give us 300, and so 430 minus 50 is 380, so that'll give us, I think, 372, oh, damn it. 372, so 12 minus 5, 0.7. So that's kind of the minimum. This is the maximum. So basically we're saying that, the mean weight, the average weight of these frogs are 430.2 grams with a margin of error of plus or minus 57.5 grams, which means that actually the weight of the frogs, we're pretty confident, fall between 372.7 grams and 487.5 grams. So this margin of error is tells us a bit about, if you will, the spread or the variability is the proper statistics term. So the spread of our estimate. And you're most likely to encounter this when you hear political polls, right? And then confidence interval is just our probability, our sample estimate represents the true population. And so confidence levels tend to be set at 90% or 0.9, 95%, or 99% are pretty common ones. So this would mean that if this were a 90% confidence level, that our frogs, so the average weight of our frogs in our sample is 430.2 grams, and that based on, there's some calculations to come up with the margin of error. We're not going to go into those, but what this does is kind of captures the spread or the variability around that mean. And so we would say that, we are, if it were a 90% confidence level, we're 90% confident that the true value of the frogs, of the mean weight of frogs in this pond falls between 372.7 grams and what I have over here, 487.5 grams. So that's, that's quite a bit of spread there. Let me talk about how those are related to each other. So for sample sizes, bigger is generally better. And this is because bigger samples will reduce the margin of error, all other things being equal.
but there are diminishing returns as you draw larger samples. And so the rule of thumb is that you reduce the margin of error by half if you quadruple your sample size. So not double your sample size. So this is not linear. This is a sort of a non-linear relation here. So if it were linear, you would just double your sample size and that would reduce your margin of error by half, but no, you actually have to quadruple it. So that would mean that, in the case of the frogs, if I had 15 and I wanted to reduce the margin of error by half, then if there really are only 27 frogs in the pond, I really can't do that because I would just end up taking a census of all the frogs, right? But in larger populations, you can do that. Though the point is that it's often becomes, this means that it's generally pretty close, not exactly, but it's useful to think that this means that the sample collecting something that's 4 times as large, useful way to think about that is that it's going to take 4 times as long or cost 4 times as much money. So you want to think long and hard about your margin of error and how much, what you want to set that at. So our margin of error, remember that's the expected range around our parameter estimate. So basically for that, you've got, in this case, our parameter estimate's a mean, and then, we figured out its minimum and its maximum, right? So that was just the mean plus the max. So that was just the positive value. And then if the mean minus the minimum gives us the lower bound on that expected range. Sometimes this is also called a confidence interval, which is super confusing because there are also confidence levels, but don't worry about that right now. So then the last of these three is the confidence level. And this is how confident that we are that the true value of the population parameter falls within our margin of error around our sample estimate. So in the case of the frogs, that's one way to think about this is that, maybe unbeknownst to us, someone else had captured all 27 frogs and found out that their weight was actually, I don't know, 412.5 grams. And so that could be, the population mean for those frogs. So the average weight of all 27 frogs. Unbeknownst to us, they had already gone on collected the data maybe the day before, or maybe even earlier that day. And, our estimate was that it's 430.2 grams is our sample mean for our 15 frogs that we acquired. And then if we take the minimum and remember then we had our margin of error, which I believe we had as 57.5. So our sample estimate was 430.2 grams. And so our true value of the population parameter is 412.5, which often you don't know, but sometimes you can. And so it's useful to kind of think about those cases when you could know, to help understand how things like the central limit theorem get created. Anyway, let's come back to this. So this means that for our sample, that our mean was 430.2 grams, but there was a fair amount of variability in those frogs' weights. Some were heavier, some were less heavy. And this means that the range that we're confident about is between 372.2, is that right? Yeah, 2 grams on the low end, and on the upper end, actually earlier I calculated this wrong. I think I had 487.5, it should be 487.7 grams. So we end up with this range here around 430.2 grams. And sometimes it can actually literally help to just draw a number line. So we've got our mean right there. So 430.2, and then over here, and we'll pretend those are equal distances. So this would be 487.7, and this would be 372.2, right? So this is our sample mean, our sample estimate. This is once we take the margin of error into account between 372.2 and 487.7. So that margin of error means that we are, when we have our confidence level, remember that can be like 90%, sometimes people write it as 0.9, or 95, sometimes people will write that as 0.95 or 99. Then, which sometimes people will write as 0.99. And these are conventional levels at which confidence intervals are set. The dude who invented these originally said, you know, it could be a lot of different things, but I'm going to use these 3 levels. And so you pick your level. We were pretending that we had a 90% confidence interval. So what this means is that we would be 90% confident that the true value of mean frog weight, so this would be the mean weight of frogs in that pond, you know, it falls between 372.2 grams and 487.7 grams, right? So this is the way you want to think about these estimates, is that they're really a range. It's not, oh, it's 430.2. That just happens to be in the middle. That actually we're 90% confident that the true value of the population mean, which in this case I was going to assume is 412.5 grams, you know, falls between this lower bound and this upper bound. And so 412.5 grams would fall on this number line, kind of like right over here. So that might be a way to think about it then, right? So there's 400. So that's the true population mean, whereas our sample mean was 430.2. But once you take into account this margin of error, it actually does capture the true population mean. So that's the confidence, sort of how we make use of the margin of error and confidence level. And this means that we're 90% confident that the true value falls between here and here, and 1 time in 10, the true value would be expected to fall either, you know, over here in this lower bound. So it would fall outside of that interval, either below that interval or above that interval. So that's what that stuff means.
Okay. While Spicker doesn't show us the formula for how these relate, so how sample size, confidence level, and margin of error, he doesn't, I believe, show us the sample size for how these relate. He does show us a formula, or not a formula, a table. So it's useful to look at this. So he notes that bigger samples either increase your confidence level, so that might mean, so an example of that would be, you move from 90% to 95%, or they decrease your margin of error. So, in the case of where we had our frogs, we had plus or minus 57.5. We could, reduce that. If we increased our sample size by 4, then we could, I believe, that would then improve our margin of error. So it would reduce our margin of error. So it would make it smaller. So I think it would make it about 26.75 grams, right? Though that would require that the pond actually had more than 27 frogs in it. So he shows us this lovely table to help us think about this. So what we see is, in this column we have sample size. So that's a lowercase n. We have confidence level. That's often abbreviated as CI, either with or without periods, and margin of error. Nope. Jesus, no. Actually, scratch that. We don't want to say that. So here he's got ME. So we just want to call these confidence levels to stick with his nomenclature. Sometimes we'll also talk about confidence intervals over here. And so the thing to remember is that the lower bound and the upper bound basically would then capture, well, this gets us too much into probability theory. Let's not go there. Okay, so this says samples of the US population. It doesn't matter whether it's dogs or cats or fir trees or soil samples. These relations hold up for everything. So here we see we've got a sample size of 750, which it would be if at a 19 out of 20, so a 95% confidence level. So this means that 19 times out of 20, the true value of the population parameter, so say the population mean, would be captured within that bound of this confidence interval, and that, the margin of error would be, plus or minus 3.6 around whatever that value was. So if we were saying, like, if we had a survey that asked, what percentage of people love cats, we get some value. And so let's just say we'll just say cat owners. So if it is like 0.48, so if nearly half of the population owns cats, one or more cats, then under this scenario here, sample size of 750 people, randomly selected, maybe through a telephone survey. So of cat owners, or 700, so this is really then the population it refers to are people who own telephones, and not necessarily everybody, because if you don't own a telephone, then you won't get called. But for cat owner, and there was a question like, are you a cat owner? Yes or no? Then 0.48 plus 3.6 puts us a little bit over, so what is that?
That's like 51.6% to, I think, 44.4%. This is where teaching in front of human beings in the same room as you is useful, because a student will invariably say, like, are you sure that number's right? I ended up with something else. So, which is totally fine when that happens, because it proves that I am infallible. So, okay, so here then, we've got this margin of error from, if I did this right, 44.4% to 51.6%. So basically 48 plus 3.6 should give us that. So 49, 50, 51, yep, and 44 and 48 minus 3.6 gives us this. So if we double that sample size, but keep our confidence interval the same, we see that we are still 95% confident that our estimate of cat owners is 0.48, but now it is 0.48 minus 2.5, so which should give us, I believe, 45.5%, and so 50.5%, right? And so this confidence interval, this margin of error, is narrower, and so it's more precise. So the variation between the upper and the lower bound is smaller. So this happened as here we just doubled the sample size, right? If we go down here to 3,000, so 750 times 4 gives us 3,000. This is quadrupling the sample size. Oh wait, actually, let's go to this one here. So we want to make sure that we're still using the same confidence intervals, or sorry, confidence levels. So if we go to this one, so that's 750, this is 3,000. So this sample here is 4 times as large as that one. And we should then see that this margin of error is 1/2 of that, which indeed it is. So 1.8% is basically half of 3.6%. And so here then we take 48 and or 0.48 and subtract 0.18 from it. So that's going to give us 46.2% as the lower bound, and over here it's going to give us 49.8%. And so here you see how, as you increase the sample size, your margin of error gets smaller. So basically your estimate becomes more precise. But we are also leaving the confidence interval the same. You can also, so here we've got an example with 750, and we doubled the sample size. Here's the confidence level. So we see if we move from there to there, maintain the same confidence level, that this value here, so the second one, when the sample size is bigger, becomes smaller. So with 750 people and a 99% confidence level, we have a 4.7% margin of error. So that's a wider interval. If we then quadruple that, so that would be this case right here, we see that. So they rounded up on this one, but from 4.7 to 2.4, basically this 2.4% after the rounding, so these are both rounded, this is essentially half of that. So there we see what happens with a wider confidence or a higher confidence level when we increased the sample size, that as long as we hold the confidence level constant, but we increase the sample size, our margin of error shrinks as well in these cases. But what you will notice is that, I guess the point is that if you want to change your confidence level, so as soon as you change your confidence level, so here we had 750 and 750, that wider confidence levels are associated with bigger margins of error, I guess is really the point here. And so if you want to increase your confidence level more so than you want to increase your margin of error, let me use a different color for this, try purple. So we start out here, right? And we want a wider confidence level, and we're not concerned about margin of error. Well, then we can just move from that to this, but then our estimate, this confidence interval, becomes wider. So here, if it's 4.7, so basically 0.48 minus 0.47 gives us, I want to say 42, no, fiddlesticks, 42.3%. Yep. Wait, so 3. Nope, that's wrong. Hold on. Hold on. So 48 minus 4.7. So 48 minus 4 is 44. Okay, yep. So that will give us 43.3% to 48 plus 4.7, 52.7%. Maybe this purple. Yeah. So this here in purple shows you what happens if you don't change your sample size, but you change your confidence level, that actually your margin of error becomes even wider. So that's, I'm trying to illustrate the point here about the trade-offs between these two, and I'm sure I've flogged this horse to death. So let us proceed. The point about all of this that I want you to really take home is that you only need random samples if you want to make an inference about a population. In other words, if you want to generalize from quantitative data from your sample to the population, then you need a random sample. If you don't want to generalize, and technically I suppose you could do this with qualitative data, but that's a lot messier. Like, this is almost always with quantitative data that you want to do this. You know, if you don't want to generalize from your sample to the larger population, that's fine. And then you don't need a random sample. The point here is also that you almost never need random samples for qualitative data. So if in your proposal you tell me that you plan on conducting a random sample for your interviews, as in, you know, I will conduct a random sample of individuals, you know, from a particular sampling frame to ask them these questions, but all you're asking are largely, open-ended questions, I am going to want a justification for why that is. Alrighty, so that blathering was all about random samples. Now let's move on to non-random samples. And there are actually, with random samples, there are a couple of different ways to do those as well. I think I'd touch on those next week, but we'll leave that as is. For non-random sampling, there are a variety of procedures. Different books will use different terms for these, so I'll kind of touch on these. But the thing that you want to remember about non-random sampling is that it provides a weak basis for generalization beyond the sample, right? So if you want to generalize from your sample to the larger population from which it's drawn, you need a random sample. If you're not so concerned about that, then you can use non-random sampling. And in a lot of cases, you won't be concerned about that. You'll be more concerned about the experience of people who are just in your sample. That's totally fine. The benefit of non-random sampling is that usually it's easier to draw the samples. And, it's going to produce statistically biased samples, which just means that every element in the population doesn't have an equal chance of being selected, but often that's not a problem. So the first and most common, the first kind that Spicker talks about, and the most common that I've seen, certainly mentioned in students' proposals, is something called accidental sampling, or sometimes it's known as convenience sampling. So if you stand outside the door of a store and stop people and ask them to complete your survey, that's generally an example of convenience sampling. In theory, if you stopped every fourth person, then you could argue, or every nth person, you could make a moderately justifiable argument that is a de facto random sample, but then your sampling frame are really just all of the people that were coming to the store, during that time that you were sampling, and not necessarily the entire population of people that use the store. It's often confused with random sampling because most people don't pay attention to what random means when we talk about sampling. Remember that random has a very strict definition here. Its findings are limited to the sample, so you don't generalize beyond the sample. But you don't really need to define a sampling frame before you start sampling. Usually, just opportunity and location determine who is in the sample. So it could be that you just start pestering people at a park if your research question has to do with, why do people use the park at Peterborough in October? And that's perfectly fine. But that would generally then be accidental or convenience sampling, unless you come up with a way to develop a sampling frame out of that. He also talks about something called accidental quota sampling. So this is a variation of convenience or accidental sampling. And you just sample until you hit a quota. So, maybe you're at a park and you want to survey, people about why they use the park or how often they come to the park, perhaps. And, you decide that you want to sample, that you want to get at least 10 people that are just sitting on a bench. You want to get at least 15 people that are, actively using the park in the sense that, they're playing a sport in it, or they're chasing their kids around or something like that. And, maybe then you also want, some number like 10 or 15 people. I'm just picking these numbers off the top of my head. People who are strolling through the park, but do not actually stop in the park, right? And so there you've got 3 different groups, and you want to reach a minimum quota just so that you get a sense of, what these 3 different groups might be, how their usage might vary. So we use it to ensure that a minimum number of observations are included from a rare group. So in that example I gave, none of those groups struck me as particularly rare, but you could extend it to, I don't know, people with pink hair or something as a rare group. Okay. Spiggart also talks about something called purposive sampling, and under this he lumps a couple of different ways to conduct non-random sampling. And the point of this is that the sample is collected with a specific kind of respondent in mind, though a respondent implies that it's a person. So you could just say a particular kind of element in mind. If you are sampling non-living characteristics in the community, say like cracks in a sidewalk. That's a bit strange. So the reason we'd want to use it is there's typical case sampling. So this is where you are interested in, finding out something about typical or common cases. So, for park users, it's probably, park users are probably people that are walking through the park, sitting on a bench, or, chasing their kids, or, playing a sport, or using a playground or something like that. It's probably not people juggling knives or flames, even though when I was younger and went to Indiana University, there would often be somebody in a park on campus who would be, I don't think they ever juggled knives. They would usually juggle bowling pins. So, and actually there would be a couple of people that would come and do this. So those I would think of as possibly as more atypical cases. So, but typical cases, sampling is one approach. Another is extreme cases. So in that case, if I thought that people juggling bowling balls or flaming chainsaws or something like that were an extreme case, I might just seek out extreme cases like that. So in some cases, you might think of extreme cases as situations that turned out, for someone, it turned out really well or really poorly for them, as opposed to what typically happens. Sampling technique that I've used, a non-purposive sampling technique that I've used, is called snowball sampling. And with this, this usually involves people. I'm not sure how this works with inanimate objects or even with animals, but with snowball sampling, you contact your initial person, and then as you are either, and usually this is with either a survey or an interview as the means of collecting the data, you then ask them if they know of other people that might be interested in participating in this study as well. So the first respondent, the first person that, replies to your survey questionnaire or who, submits to an interview, they provide leads to additional relevant respondents. And with this, you often repeat until, a couple of things happen. So data saturation, so you keep hearing the same thing, or you've run out of time, or you've run out of money to support the sampling endeavor, or all your leads run out or dry up. And so you use this I use it just because I find it an easier way to get access to other people that will then that you'll kind of come recommended. So, if I interview one person and at the end of my interview, I ask, like, do you know of other people that might be interested in, that might have had a similar experience and may well be interested in participating in this, in my interviews? And, then they'll say, oh yeah, Joe Blow and Sally Mae and blah, 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 maybe a couple of other names. And, you make sure that you find out it's okay that you say, I interviewed I interviewed Bob Smith, my first respondent, and Bob said that, you, Sally Mae, may well be interested in participating as well, given that you've had a similar experience, right? So that's why I've used it, but it's actually really useful for getting at secretive or obscure groups that are hard to find and don't have a lot of public visibility. So another sampling procedure, a non-random sampling procedure that he makes reference to, is called systematic matching sampling. And so with this, you systematically pair each observation with another that varies on only one characteristic. So it might be that I'm interested in the impact of location on ice cream sales for ice cream stands, right? So I might decide that the characteristic that I want to vary is location. So some ice cream stands will be in sort of high traffic areas and others will be in lower traffic areas. And so that locational characteristic could be the one that I let vary. And so then I try to find, okay, here is an ice cream stand that is similar to this other one in so much as, maybe the kinds of stand that it is. It's wheeled, that the person shoves it around like a push cart. And then it might be another set of observations are ice cream trucks that I think are, some frequent more high traffic areas than do others. And so for each observation, I try to find another one that's similar to it in all ways except on one characteristic, right? So maybe I want to look at, the effect of gender on ice cream, on the experience of people who work at ice cream stands. And so, I locate someone who is male and is operating an ice cream stand and someone who is female and is operating an ice cream stand, but they're in a similar location, right? So, and then I go to maybe a lower traffic location and then I repeat that. So finding a male and finding a female. Or a transgender person, right? So that could be a bit trickier though. Anyway, so, but you've got one characteristic that you vary in your pairs, or I guess in some cases I don't know what the triple, T-R-U-P-L-E, I think is like a three-way pair. Yeah, so that you have that kind of variation. And so you would use this to control for variation, because it could be that the experiences of men and women vary, or it could be the experiences of ice cream operators located in high tourist or high traffic areas differ from those in low traffic areas, right? So for this, you'd want to think about what are the factors that might, be important for explaining differences in the responses that you see. It can also be a way to compare the experiences of members of a rare group to a more common group. So you might, if you're interested in job discrimination based on race, you might interview people who have similar credentials, went to the same school, have the same major, and then the only thing that's different is that, one's from a visible minority group and the other one isn't. So. And I will stop here. Sorry this took so long. This lecture is a bit longer than the others, but I hope this helps you better understand the material and have a better sense for yourself of the kinds of sites that you might make use of for your research proposal and how you might collect data from those sites.